So we know what a simply connected domain is, and we've discussed conservative fields, and there's one additional thing to say about conservative fields in simply connected domains, and it turns out to be the most useful and most important part of this discussion. So let's remind you what we already know. So we started out with, we're back in 2 dimensions. We're going to extend to 3 dimensions a bit later. We need some more preparatory work. We're back in 2 dimensions. So fxy is a continuous field, only continuous, over some domain D in R2. This is all our assumptions so far. And the theorem that we had said the following, that the following properties are equivalent. Remember this abbreviation. The following are equivalent. 1. F is conservative. And by this we mean the integral over any closed curve, gamma, the line integral, is 0 for any closed curve, gamma. Remember that definition? The second property was 2, the integral, the line integral of f, over any path connecting 2 points A and B, and we indicated that like that, does not depend on the path. It only depends on the endpoints. So does not depend on the path connecting, or let's say from A to B. So this was equivalent. And the third equivalent property was that f has a scalar potential. So f is the gradient of some scalar function, which we denoted phi. And let me add, in which case we proved this, the integral of f over any path AB is none other than the difference in the potentials between the endpoints of the path. Okay, so everybody remember these equivalent properties? Okay, so now I want to add a number 4 here. And then we're going to do examples. We didn't do examples of this, but this number 4 is the key to doing examples usually. So, but number 4 is going to require an additional assumption. Okay, so, or actually 2 of them. If f is in C1, so this is an additional assumption because for these 3, all we assumed was that f was continuous. So now we're assuming more smoothness. Okay, we're assuming that the field is C1, meaning that its components, P and Q, are C1 functions, scalar functions, meaning that P and Q both have both partial derivatives continuous. Okay? And so this was an assumption about the field. Now there's going to be another assumption about the domain, D. And D is, and guess what that assumption is going to be? Wild guess. Just throw a wild guess. Wow, how did you think of that? Cool. Is simply connected if f is C1 and D is simply connected, then also So by also I mean that these three properties are equivalent to a fourth property. Remember, by saying are equivalent, I mean that each one implies the other. They're all if and only ifs. 3, if and only if 4, if and only if 1, if and only if 2. They're all if and only ifs. Also 4, and 4 is qx equals py. Remember, f has two components, p and q, and the fourth property is the derivative of q with respect to x equals the derivative of p with respect to y. Okay? So what I want to do first is to prove this. To prove, so the equivalence of 1, 2, and 3 we discussed. We didn't prove everything. We didn't prove how to construct a potential function if we know that the field is a conservative field. That's a bit harder, and we didn't show the details of that. But other than that, we show that these three are equivalent. Now I want to show the equivalence to 4. In order to show the equivalence to 4, I need to show that 4 implies any one of the three, and that any one of the three implies 4, right? That's showing the equivalence to 4, right? Okay, so let's do that, and I'm going to start with the direction. I'm going to assume 3 and prove 4. So my assumption is going to be, it's going to be on another board, that's why I'm saying stuff here, and then we'll move and write it on the other board. I'm going to assume that f is the gradient of some scalar function. F has a potential, and I'm going to prove that the components of f, p and q, satisfy this under the extra assumptions written here. So let's do that. So this is 3. So this is proof of the fourth part. So 3 implies 4. So assume, now that our assumption is 3, that f is the gradient of phi, some scalar function. What does that mean? All that means is that the gradient of phi is the derivative of phi with respect to x and the derivative of phi with respect to y. That's the gradient, right? The components of f are p and q. Saying that these two are equal merely says that p is the derivative of phi with respect to x, and q is the derivative of phi with respect to y. Do you agree that that's our assumption now? That's our starting point. What do we want to prove? We want to prove that the derivative of q with respect to x equals the derivative of p with respect to y. Well, what's the derivative of q with respect to x? Q is this thing. The derivative of d phi to dy with respect to x is, let's use this notation, the derivative of phi y with respect to x is phi y x. Do you agree? Since f is C1, this is our additional assumption now, f is C1, this thing is a continuous function. It's the derivative of one of the components of f. That's what C1 means. Therefore, this second derivative of phi is continuous. This is the mixed partial of phi, right? But we know that if the mixed partials, if the second derivatives are continuous, then the mixed partials are equal. Remember that theorem? So this equals phi x y, which is the derivative of phi x with respect to y. But the derivative of phi x with respect to y is just py. Did everybody follow that? Clear? Good? So that proves 4, assuming 3. Okay? What didn't we use? Right, we didn't use the simply connected, and it's not a mistake. This direction does not require the simply connectedness of the domain. Okay, so let's remark that. This direction, the implication of 4 from 3, does not require D to be simply connected. Okay, so you can guess that the other direction is, otherwise we wouldn't have put it in the theorem. So let's prove the other direction. In the other direction, I want to prove that 4 implies one of the 3 equivalent ones, and I'm going to show that 4 implies 1. Okay, so here's the other direction. 4 implies 1. So now I'm assuming, okay, so our assumption is that Qx equals Py. Then, what do I want to show? I want to show that the line integral over a closed curve, any simple closed curve, is 0. That's what I want to prove. That's being conservative, right? So here's the line integral. Here's gamma. Gamma is going to be any simple closed curve. And here's our f. I want to show that this thing is 0. What I know is this. What comes to mind when you see this and think of the things we've done with line integrals? Hint, color. Starts with a G. Green, good. Okay, you could have said gold, for example. Okay, so green. What was Green's theorem? Green's theorem. What was Green's theorem? It said, okay, the line integral over gamma equals the double integral over some domain. I'm not going to call it D, because it's not going to be RD. D is the entire domain that we're considering here. Let's call it E, where gamma is the boundary of E, right? That's how they were related. So gamma was the boundary of E. And here, what was the function inside this double integral? It was Qx minus Py. This was precisely Green's theorem. Remember that? And if Qx equals Py, this thing is 0. Do you agree? So what did we show? If Qx equals Py, then the integral of this field over any closed gamma, closed, is 0, which is precisely 1. That was the property of being a conservative field. Do you agree? So that wasn't too hard. It was very straightforward. Where did we use f being C1 and the domain being simply connected? Answer, right, in Green's theorem. That's where we used it. Green's theorem required, first of all, it required the field to be C1. So that's where we used f being C1 in this direction. And the second thing it required, the whole idea here was that the domain we're looking at, in this case E, has to have gamma as its boundary. Okay? So this is precisely how we define simply connected domains. So let's write here and then go one board back. Green's theorem is valid since F is in C1, and D is simply connected. Now let's look back. This is a leftover from the discussion of simply connected domains in the previous clip. Let's look why that's what we need. We want to take a gamma inside D. In this case, for example, D is the ring. This is not in D, this hole here. We're taking a gamma. We want to show that the integral over this closed curve gamma is 0. For that, we want to apply Green's theorem. And for Green's theorem, we need gamma to be the boundary of some region in the domain. But if the domain is not simply connected, gamma is not the boundary of some region in the domain, and we cannot use Green's theorem. Do you see that? If we want to say, okay, it is the boundary, it's the boundary of this thing, that goes out of the domain, and F is not defined there, right? F is only defined on D, and is known to be C1 on D, okay? If we're in a simply connected situation, then D is where F is defined. Everything is C1 and works for the theorem. We take any gamma, it's the boundary of some E, and Green's theorem applies. Is that clear? Do you see why we need the simply connected in order to use Green's theorem? Everybody good? Questions? Yes?
Well, we did the Schwarze-Euler theorem with the...
The what? Say that again?
The Schwarze-Euler theorem with the mixed partial derivatives equal to each other.
Okay.
Didn't we say they has to be FC2? Like they belong to C2?
Okay, so you're asking about the previous direction of the... let me postpone that question just for a second, okay? I'll answer it. Is this direction clear? The direction in which we used Green's theorem and needed. It was essential that we have the domain simply connected in order for us to be able to take the inside of a curve gamma and say that gamma is the boundary of a domain inside the big domain D. Is that clear? Everybody? Okay. So what you're asking about is the previous direction. In the proof of 3 implies 4, right? So, and you're saying for that we need, for the mixed partials to be equal, we needed C2, not C1. But what is C1 here is F itself, okay? So F being C1, F is these things. P and Q are the components of F. They're C1, right? So the first order derivatives of phi are C1. That means that they have continuous partial derivatives. So phi is C2. Okay? This is C1, so its derivative is continuous. Okay? So phi itself is C2. Does everybody see that? Okay, is that clear? So that's why we have this mixed partials here. Clear? Okay. So this wraps up the theoretic discussion. Let's go back to the theorem. This wraps up the theoretic discussion of being a conservative field. Okay? And what I want to do is some examples. Maybe we'll do it in a separate clip, but let's just say the idea. What we're really interested in is number 2. We want to calculate work on curves. Okay, that's what we're interested in calculating. Okay, you want to calculate things like this. If we know that the field is conservative, then there's a very easy way to do it. This is the way to do it. We don't care about calculating the line integral, parametrization and whatnot, and calculating integrals. We don't care. It's all disintegrated. All we care about is the value of the potential function at the 2 endpoints. Subtract them and you have the line integral. Do you see that this is very convenient? It simplifies life a lot. Okay? So if somebody gives us a field and tells us to calculate something like this, the procedure that we usually go through is the following. First, we have to determine if the field is conservative. And the easiest way to check if the field is conservative is number 4. This is very straightforward. You take the derivative of q with respect to x, you take the derivative of p with respect to y, check if they're equal. If you got the same thing, this is just taking partial derivatives, very easy. If they're equal, good, it's conservative. If it's conservative, it has a potential function, and that we need to find, and it's very easy to find potential functions. That we're going to see in examples. Once you have the potential function, you keep it in your pocket, and then no matter what curve you're asked about, it's very easy to calculate the line integral. Clear? So that's kind of the scheme that we're going to do in examples in the following clip.